Hello, and welcome to Science Journeys, Caltech's first online science education series. I'm Michael Alexander, the Director of Caltech's Public Programming, and I'm very happy to have you all with us today. Caltech is one of the nation's premier science education and research institutions. In fact, Caltech created the Jet Propulsion Lab, JPL, which has managed most of the United States' unmanned space flights. As we speak, there is an unmanned space mission on its way to Mars that includes a helicopter that will be the very first to ever fly on another planet. Our office is also responsible for bringing to the campus the Performing Arts series that takes place here in Beckman Auditorium. We would encourage you all to look to our website, where you can find out about all of the lectures and performing arts series that are going on here by going to events.caltech.edu. I'm proud to introduce Michael Mazza, one of Caltech's outstanding science scholars. He is a member of Caltech's Visiting Science Program, a program that has been bringing science education into Pasadena area classrooms. Michael is a Caltech grad student who has been doing some very interesting research work on our campus. Today, he is reaching our new and enlarged audience via the internet, as we're all adjusting to working out of our homes during the pandemic. Michael is going to show you pictures of some of the tallest buildings on Earth and help us understand how the strength of the smallest components of the materials that are used in those buildings makes it possible to build these structures. Michael is involved in the discovery of new materials and has told me that there is still much left to be discovered. Today we're going to learn about carbon, which is all around us, and there are scientists discovering new uses for carbon every day. We're very pleased to feature Michael Mazza in our first series aimed at middle and high school students. And now, here's Michael Mazza.
Thank you for that introduction, Michael. My name is Michael Mazza. I am a fourth-year graduate student at Caltech, and my talk is titled From Pencil Lead to Skyscrapers, Building the Future with Carbon Nanomaterials. So a few of the questions that I want to address today and to get you all thinking firsthand is, what materials do we use to build the world? And how do we build the world? How does the shape of a building material change its function? Primarily, on the slide in front, we have a picture of the building Taipei 101, which is in Taiwan, and at one point it was the tallest building in the world. And it's a great indication of the super tall buildings that we're starting to see more and more of that are built primarily out of steel. And Taipei 101 is particularly interesting because Taiwan has a ton of storms, it has very high winds, so to build a building as tall as Taipei 101, we've really had to stretch the limits of what we know about structural engineering in order for it to stay standing. Why do some materials conduct electricity while others don't? What will future computers be made out of? And what are they going to look like? Another image you can see in front of you is an image of an Intel processing chip, kind of the same one that you would find in your computer, in your phone, that kind of powers the digital age today. Lastly, we're going to talk a little bit about color and how the shape of a material on the nano scale can change the color of the material. And so you can see on the slide as well, you can see the morpho butterfly with these really striking blue wings. And those are actually dictated by a process called iridescence that we're going to talk about at the very end. So first, a little bit about me. I grew up in Los Angeles. I'm from the San Fernando Valley. I first got exposed to science primarily through talks like this, and through videos, and through going to museums like the Natural History Museum and the California Science Center. And I would go with my grandfather because when he was in town, we would love going to these museums. But usually we would go when he was kind of tired of me playing video games or watching TV. So he'd throw me in the back of the car and we would go to any of the museums around Los Angeles. And our favorite was the Brea Tar Pits shown in front. And now I am a fourth-year graduate student at Caltech. That's 20th grade for anyone who's counting. However, I don't stay in classes all that much anymore. When you're a graduate student, when you're in a PhD program, you're mostly working in a lab day in and day out, and you're kind of building new materials and trying to address new questions and really get a handle of how to do science. And so I primarily study how the surface of materials, how defects on the surface can change the chemistry of the materials themselves, Chemistry labs aren't oftentimes the most glamorous places. So I have a picture for me when I was in college in an earth science lab where we had a metal plate in the middle of a field and we would strike it with a hammer, and we had a bunch of sensors on the ground away from it, and we would see that shock wave, that vibration travel through the ground. And so that's what you can see in the picture in front. Is a picture of me with my grandfather and grandmother at my college graduation. And as well as research at Caltech, I am a founding member of the Visiting Scientist program that Caltech runs, where graduate students and postdocs and staff at Caltech develop curricula based on the California science standards, and we actually teach in local Pasadena elementary schools. So I have worked with this program for 4 years. I teach the 5th grade at Madison Elementary, and that's a picture of me with only slightly more hair about a year ago. And on the right is a photo of me and a lot of my lab mates and our friends at a Dodger game last summer. So how do we build today? To go back to that first question, we continue to make huge scientific advancements, faster computers and taller buildings, but these advancements are mostly done by improving the quality of the materials and advancing the science of these same materials, steel and concrete or silicon computer chips, as you can see, not really as much by discovering new and better materials. So scientists today are actively working on and trying to develop and discover new and exciting materials to make products cheaper and make them go faster and taller buildings than ever before, to really push the limits on what we can build in the future. So let's talk about carbon. What is carbon? Well, carbon is element 6 on this periodic table, which you might be most familiar with as that thing in the back of your notebook or textbook that you haven't really seen anything about yet. It's an element, which is a type of atom, and atoms are the fundamental building blocks of nature, of all things. And carbon is an element with 6 protons and 6 electrons. And it's considered the building block of life because carbon atoms make very strong chemical bonds with themselves and with other elements such as oxygen. Carbon is also the primary element in plastics and gasoline and oil, and the primary building block of plants and all life. As you can see on this thing in front of you, this complicated molecule that you can see on the bottom left is chlorophyll. It is the component in plants that allow them to absorb sunlight and perform photosynthesis so they can get food. And at each one of those intersections on the molecule where it's not labeled is a carbon atom, and it's made with carbon and oxygen and even a magnesium. But the primary building block of chlorophyll is carbon, and it's the material that gives plants their striking green color. This is different than a carbon footprint. You might be familiar with the term carbon footprint because we talk about how much carbon dioxide, or CO2, is put into the atmosphere for a given process, like driving your car. We call that a carbon footprint. Carbon itself isn't a bad thing. It's really, really important. When we talk about carbon footprint, we're really only talking about carbon dioxide. Now let's address some other terms, right? What does nano mean? You've probably used it, or you've probably heard it used around for to mean things that are very, very small. But nano is a very specific unit. It's short for nanometer, which is the unit of measurement that is 1/billionth of a meter. So in front of you, you can see the scale of a couple of different things. So a person, a human being, is about 1.5 meters tall. The ladybug is about 0.01 meters, so 1/100th of a meter, or 1 centimeter in size, which means that about 150 ladybugs stacked on top of each other would be about a person. Smaller still is the width of a human hair, which is about 50 micrometers, or 50 millionths of a meter. And these are the smallest hairs you can find in your body, and they're extremely thin. They're probably some of the smallest things you can hold in your hand. However, nanometers are 1,000 times smaller than that. So something that's on the nanoscale, something like 5 nanometers, is actually 1,000 times smaller than the width of a human hair. And atoms are only about 10 times smaller than nanometers themselves, single units. So we're really talking about building stuff from the ground up when we're talking about nanoscale, really playing with what those individual atoms are connected to. And so we're going to talk about, as we said, carbon and the structure of carbon. So when scientists talk about chemical structure, they're talking about the very specific way that atoms are arranged in molecules and in systems. And it's the arrangement of chemical bonds that connect the atoms in a given compound. Pure carbon itself is found naturally in the Earth as 2 very different materials. One of them is graphite, where each individual carbon atom is bonded to 3 other carbons. And when this happens, you get these layers of graphite that are arranged in sheets. And so if you have a pencil around, or if you can go and get one at home, I recommend you do it and take out the lead and just feel the graphite from the pencil rubbing off on your fingers and impacting a piece of paper. Very different in structure is diamond, where each carbon is bonded to 4 other carbons. When you have diamond, as you can see from this image in front of you and from any jewelry that you've seen, you can cut it in different ways to make it a really striking, shining, refractive material that looks great in jewelry. But diamond itself, because of the strength of the bonds between carbon and the structure of it, is one of the hardest naturally occurring materials. Scientists, I use diamond in my lab. However, I don't use it in its beautiful cut form. I just use it on the tip of some scribes and some surfaces so you can mark it. We actually use diamond to scratch glass and other metals because you need something stronger than that. Uncut diamond is actually a very cheap material, and it's very useful to be able to mark up anything you can. It's extremely strong. But we're mostly going to focus on graphite today and different modifications of graphite. So how does the structure of graphite affect its properties? In review, graphite is made up of these layers of carbon atoms that are extremely flat. And when pencils leave marks, it's because you're shaving off layers and layers of graphite onto the page. They're flaking off of the surface of your pencil and impacting a piece of paper. But what other properties of graphite kind of come out of this structure? It can't only be used for pencils. We're going to investigate whether or not graphite can conduct electricity. Diamond cannot. So electricity is carried by electrons, and electrons are charged particles that can travel through wires, metals, or other materials. And these materials that can carry electricity we refer to as conductors, and materials that cannot carry electricity are called insulators. Some common conductors that you're probably familiar with are gold, as you can see on the screen. If you kind of connect an electrical wire to it, you'll be able to get the electricity to pass along the gold that you see and not onto the glass nearby. Also, you're probably familiar with copper wire. Copper is also a conductor. And copper is used to connect everything from your phone charger to the wiring of some lights that light up the stage in your home. Additionally, salt water actually also conducts electricity, while fresh water does not. And you're going to learn all about that in high school. Materials that cannot conduct electricity, called insulators. Some very common ones are stuff like rubber and plastic and wood. As you can see from these plastic straws on your screen, you cannot conduct electricity through plastic straws. So some things can conduct electricity, other things can't. We're actually going to take some time now, and we're going to investigate whether or not graphite can conduct electricity. Let's take a look at what materials we have here. First off, we have a normal 9-volt battery that's going to supply the electricity. We'll have a couple of wires to conduct that electricity. And we have a normal green light-emitting diode, or as you might be familiar with, abbreviated as an LED. And so, when we connect the electrical wires to the battery, and then we connect those wires to the LED, electricity is going to flow from the battery through the wires to the LED. And if electricity flows, that LED is going to light up. If it doesn't, it's going to stay dark. So right now it's not connected. I'm pointing it at my shirt, at my chest, and nothing is lighting up. But the moment we connect this lead, it should light up. And so it's conducting electricity through the wires to the LED and turning on that green light. So let's test something. I have some graphite with me, just straight out of a mechanical pencil. So we have this long bit of graphite that you would just find in a normal mechanical pencil, or the kind of stuff that you would find in a normal number 2 pencil. And we're going to connect the circuit that we just did through this piece of graphite. So we have our normal setup with the battery, and the first wire is going to go on this end of the graphite, of the pencil lead. And if it conducts electricity, it's going to pass straight through. If it doesn't, then no electricity is going to flow and the light is not going to light up. But if it conducts electricity, the electricity is going to pass straight through the graphite to the wire at the LED and turn on the light, and point it at my shirt. So let's test it. And here you can see that the electricity is traveling right through the pencil lead and powering this light. And as you can see, when I raise and lower the pencil lead, the moment it comes in contact with the wire, it lights up. So yes, graphite can conduct electricity. Graphite has carbon atoms arranged in these flat sheets, and each of these flat sheets acts as an electron highway. This electricity can flow across the surface of graphite freely. But what if we took a single layer of graphite? Would that be better or worse at conducting electricity? Can it conduct electricity? How would you even get a single layer of this material? Because atoms are so small. So let's introduce graphene. Graphene is a single layer of atoms. These fundamental building blocks of all matter, atoms, and graphene is just a single layer of them arranged. And scientists today are investigating the incredible properties of graphene. As you can see in the cartoon on the above, it's the same structure as graphite. It's one carbon atom bonded to 3 others in this kind of honeycomb or hexagon shape. And directly below that, you can actually see a super powerful microscope image called a transmission electron microscope that can actually see the individual atoms arranged in graphene. And so you can actually see on your screen those white circles arranged in the exact same pattern that we expect from graphite in graphene. Those are actual atoms that you're seeing. So with some of the incredible properties of graphene, it is much more conductive than copper, as it is, because we have this single layer of carbon atoms that act as a highway across. It is extremely conductive. The very strong chemical bonds that carbon makes to itself make graphene one of the strongest materials ever discovered, and it's extremely flexible. And so the thing you're probably asking now is, Michael, why aren't we using it for everything right now already? So why isn't it taking over? Well, actually, graphene cracks. And when you have a material that you build on the nano scale, on the billionths of a meter scale, it's really hard to get that perfect material to scale up all the way to centimeter scale, ladybug scale, or even human scale. And so if you actually see on this image, it's another transmission electron microscope image, you can actually see this kind of crack, this imperfection, this defect in graphene. As you can see the individual bonds again, and it's going from the top left to the bottom right, and that acts like the seam of a shirt or the tear-apart edge of a tearaway notebook, that perforated edge that your paper kind of rips perfectly down, or hopefully rips perfectly down. It never worked all that well for me. And you can actually see something like that in the structure of graphene. So take a look and see if you can see this kind of crack going from top left to bottom right. And thankfully, they indicated it for us as well. So you can actually see that the bonds aren't right. There are a couple carbon atoms that are out of place, or a couple of bonds, maybe too many carbons, maybe there are 7 in a ring instead of 6. And so these things cause graphene to rip apart really easily, and the incredible properties of graphene that we see on this nano scale are really dependent on not having these defects. And so it becomes incredibly difficult to make these, these super small, astonishing new materials into, translate their properties onto the human scale. And actually, this kind of studying of defects in graphene is actually what I often work on, and what I have spent a lot of time on is looking at the chemistry of these imperfect regions and how they actually react differently than these perfect regions nearby. Graphene, however, still has some everyday uses. It's actually used commercially. You can buy products that have graphene in it. It's currently found in bike helmets, and it's also found in headphones because graphene is so light and so flexible. It's really useful in high-quality headphones and earphones where they can kind of vibrate like a speaker and kind of really create high-quality sound. It's also still being investigated for flexible electronics. You have an electrical circuit like a computer chip, but you can kind of bend it and you can kind of put it on plastics and it'll bend and continue to function. So this is often being investigated for wearable electronics, so electronic equipment that you can keep on your body, so that when you flex your arm or you move around, the circuit doesn't break. Let's move on to another type of material, what can we build with this? So recall when we talked about conductors and insulators, we don't really want a flat sheet to conduct electricity. We'd really want a wire, like a copper wire. You know, when you connect your phone to an outlet with a charger, it's connected by a one-dimensional electrical wire that you use. So let's go back to the basics of graphene. Can we make something like a wire out of graphene? So let's go back. Carbon makes really strong bonds with itself, right? Graphene itself is very flexible. So what can we do? Well, imagine this is our nice little graphene sheet. What if we just took this and folded it over on itself? Then we've taken a super flat material, that electron highway, and rolled it into a one-dimensional wire, like a copper wire. You can make something called carbon nanotubes, which are just single layers of graphene that have been rolled up and now form a one-dimensional wire, like a copper wire. And these are extremely flexible, and they're still electrically conductive. So we have one more transmission electron microscope that you can see on your screen, and that is something called a multi-walled carbon nanotube, which is a bunch of layers of graphene, or a few layers of graphene stacked on top of each other and then rolled. So you create kind of like an onion structure, where you have layers and layers of nanotubes kind of on top of one another. And you can see that in this microscope image. You can see these flat layers corresponding to each kind of ring in this carbon nanotube, kind of like a tree ring, where you see these concentric circles around a center. That's exactly what carbon nanotubes are. So with carbon nanotubes, we can now make extremely flexible wires made of only carbon, extremely strong and lightweight cables for construction, because as you remember, graphene is extremely strong and flexible. So let's talk about construction. Let's talk about building materials right now. What kind of materials do we use today that we need strong and flexible cables for? We use steel cables. We use steel cables on everything from aircraft carriers to ski lifts, right? They are everywhere. But is the shape of the cable important? Let's take a look at the shape of the cables that we use on the human scale and larger today. We braid them. So braided steel cables are very flexible and can be used to catch airplanes on aircraft carriers or shuttle skiers up mountains. So this is an important point that scientists use when we're looking at really small-scale materials. Our understanding of the world as we know it on the human scale can actually inform our understanding of these things that are 1 in 1/billionth the size of you. So let's take a look at a video, and it's a video of an arresting gear on an aircraft carrier. And so I want you to look out for two things. I want you to look out for the shape of the cable, and I want you to look out for what happens when the aircraft actually contacts this wire. Arresting gear are the equipment that is used to literally catch an airplane when it's landing on an aircraft carrier. And so these aircraft have kind of hooks on the back, and they catch these wires, and as this plane comes in to land, these wires have to yank it down and slow it down while it's still on the surface of the aircraft carrier. Let's take a look at these wires in action, these arresting gears in action, and take a look at how flexible they have to be and how strong they have to be. Right there. Can you see that in the bottom left? You can see these wires, these steel cables coiled around one another. They're braided, and that makes them very flexible and very strong. Strong enough to wait for it. There. Look at those cables snap into place and follow the plane the moment they make contact and slow it down as quickly as possible. These cables are actually the exact same thing that are used to shuttle skiers up mountains. This is a picture of Mammoth Mountain, which is a skiing mountain in California, because these wires need to be flexible so they can actually take the shape of the mountain and take people up these really steep slopes. And that's exactly what people do on the nanoscale. So scientists are working on ways of taking these extremely small nanostructures and turning them into useful materials by literally spinning them into fibrous bundles. As you can see by this microscope image on the right, this is a different type of microscope. This is a scanning electron microscope. And you can see all of these carbon nanotubes that are pointed upwards literally being spun into a fiber. And you can see these fibers that look like braids. They look like chains. And they are extremely compact. They're made of hundreds or thousands of these different nanotubes, and they are still over 10 times thinner than a human hair, that first image with the arrow. Still 10 times thinner than the smallest human hair, and they're made up of hundreds of thousands of these super small wires that are extremely strong. And in fact, these specific wires are almost as strong as bulletproof vests. We're going to talk about another application of carbon nanotubes. There are actually several applications of carbon nanotubes that I would like to talk about, but in brief, carbon nanotubes are also being investigated in the medical community. Carbon nanotubes have been shown to be able to selectively target cancer cells so that they can actually eradicate cancer cells instead of healthy cells as well in a kind of targeted medicine. But today we're going to talk about color. And objects and dyes have color because they reflect a certain amount of light and absorb other colors. A purple shirt like I'm wearing today appears purple because it absorbs all the other colors except purple, which it reflects back into your eye. And brighter colors reflect a lot of light, like a bright yellow or a bright green, and darker colors like a brown or a gray absorb a lot of light, so they appear darker. Carbon nanotubes are being today to develop a very specific and unique type of color, and we call that superblack. Dyes and paints appear black, like my black pants today, because they absorb all types of light, and they absorb about 95% of all of the light. Carbon nanotube arrays can actually absorb even more, 99.965% of all light. That is 100 times darker than your black shirt. And how does it work? It works by trapping the light. So, let's take a quick detour. If you're playing a game of pinball, and you hit a pinball up to the top and it bounces across those bumpers as shown. Each time it hits one of those bumpers, it's going to lose a little bit of speed, a little bit of energy, and it's going to slow down little by little until it just falls back. Each time it hits one of those bumpers, it loses energy, slows down. That's exactly what carbon nanotubes do to create these super black materials, like these vertical-oriented nanotubes, so they're pointing straight up and it looks like a forest. And so when light comes down and it hits these structures, it doesn't go into the tubes, it goes past the tubes, and it kind of acts like a pinball machine. The light bounces back and forth among these tubes and it can't get out, and each time it gets deflected and bounces off these tubes, it loses a little bit of energy. But light is the fastest thing in the universe. It does not slow down when it loses energy. It actually changes color. And so as it slows down, it changes color and loses energy until it becomes infrared radiation, what we call heat. And heat can be absorbed by these nanotubes. So it's not just reflecting light away from your eye. What it's doing is slowing down the light. It is lowering the energy of the light, taking that energy away from the light as it's trapped until it is absorbed as heat, and that does not escape. And so this is what this material looks like. The result is called Vantablack. And so scientists have a bunch of fancy abbreviations and terms, but oftentimes we just come up with different names to describe what we're seeing. And so Vantablack is a product made by a company, and it stands for Vertically Aligned Nanotube Array, Vanta. It can absorb 99.965% of all the light, and it's so dark that it tricks your eye into almost thinking it's empty space. Look at the image on the bottom right. It's kind of spooky, right? It kind of looks like that person has a hole in their hand, but they're just holding a material of Vantablack because it absorbs so much light. And Vantablack and other super black materials are actually being used and investigated right now to line the inside of telescopes. So you want as little light bouncing around in a telescope as possible. You want only the faint star or the planet that you're looking at. And so any other light that gets bounced around in there is going to mess up your image. So if you have a super dark material that's absorbing all your light, you can see fainter and fainter stars and further planets. And lastly, I want to talk about structural color. So this is very cool. So materials of the nanoscale can also scatter light in addition to absorbing or reflecting it. And so when I mean scatter, so when light hits a surface, it can bounce back and it can go into your eye, but also some light scatters and it kind of gets deflected away and it doesn't return to your eye, so you see something different. And these nanomaterials scatter certain colors of light and not others. And so my friends and coworkers in my lab actually work on this. They create these nanostructured materials that you can see that have a long kind of squiggle shape, but they're only pointed in one direction, and they kind of look like nanotubes, like blades of grass pointing upwards. And And these materials, when you actually change the angle at which you're seeing them, as you'll see in this video, they'll reflect a different type of color, a different color of light. This is called iridescence. And if you were to take the butterfly wings from the first slide, and you were to look at them under a microscope, they would look similar, but not exactly the same as what I'm showing you right now. Structures that are patterned on the nanoscale can have very striking colors, and they can change color based on a number of different properties. So let's take a look. And as you can see, as the chips with these structures on them are tilted back and forth, they change color from red to blue. So let's review one last time. The element carbon has many fascinating properties that change depending on how it is bonded. Graphene, which is a single layer of graphite, a single layer of atoms, is extremely flexible and conductive and is already in commercial products. And we can make nanotubes out of graphene that are stronger and more flexible than steel, and we can spin them into fibers. And they're already being investigated in the field of medicine. And we can build nanoscale patterns that change the color and absorb nearly all the light that hits it. So let's go back to that first question. How do we build the future? We will design the materials from the nanoscale all the way to the human scale and even beyond. We will create new materials, patterns, and structures to accomplish things we haven't even thought of yet. And that last step, that's all up to you. The next generation of scientists, the people I'm talking to right now, are going to address problems, investigate new materials that people like me have never even thought of yet. How far we go is up to you. Thank you all so much for coming to the first installment of the Real Science program. The materials that I have used and all the resources that I use on each slide are credited here, and I look forward to all the questions that you may have.
Thank you, Michael. Thank you for a wonderful talk. If any of you have questions, you can go to the link on this website and post your questions. He will be responding online within 48 hours of the premiere showing of this lecture. I also want to thank Mitch Aiken and Kitty Cahalan of Caltech's Teaching, Learning, and Outreach Office, as well as Mary Herrera from the Office of Public Programming, and the entire Academic Media Technology team and the team from Event Productions. And thank you to the Caltech Employees Federal Credit Union, the Friends of Beckman Auditorium, and our many sponsors who make these types of programs possible. We look forward to your joining us again for other performing arts events and science lectures, which you can find out about by checking our website, events.caltech.edu. Thank you for joining us.